So in this chapter, we have primarily focused on covalent bonding, where electrons are shared between molecules. And that is one of the most important types of bonding that we have in chemistry, and so that's why we spend a whole chapter talking about it. And in the previous video, we just looked at the strengths of covalent bonds. How much energy does it take to pull apart the atoms if they're bound together by these shared electrons? But in this video, what we're going to look at instead is thinking about ionic bonds, where electrons are not shared anymore, but rather they are pulled apart from each other. So you can think of this as where electrons are being stolen from one atom to the other. And what holds these together, these compounds together, is different than what holds together covalent bonds, right? Covalent bonds in something like nitrogen that we've just been looking at, it's these shared electrons that hold the molecule together. And so to get the molecule to be pulled apart, you actually have to put in energy to pull those electrons away and let the atoms separate from each other. In something like sodium chloride, first of all, if we want to draw a Lewis structure, even though it doesn't make a whole lot of sense to draw Lewis structures for ionic compounds, but if you did, what we would see is that chlorine would have an octet and sodium would have no valence electrons, because it's one electron that it had got donated to the chlorine, and so it's not there anymore. The chlorine took that extra electron from sodium. Sodium gladly gave it up, so that sodium could also have a complete octet. In this case, it gets a complete octet by getting rid of an extra electron. In chlorine, it needs that extra electron, and so it steals it from the sodium. So this is what a Lewis structure for an ionic compound might look like, but doesn't really reflect what's actually happening, because, of course, we have this crystal structure where we have a bunch of sodium and chlorine all next to each other. And what holds them together is the fact that you have these positive and negative charges pulling on each other, right? So there's the attractive force between these. And this is what's reflected in terms of the strengths of ionic bonds. So we have an equation in physics that describes how positive and negative charges interact with each other, called the Coulomb's law. And this is what will tell us how strongly these different ions are held together. So in Coulomb's law, the force that holds these things together, or the energy that's associated with it, is proportional to the two charges, so charge 1 and charge 2 multiplied together, divided by the distance between them. There's some other constants in here, but this is the important part of Coulomb's law. So how is this actually reflected in terms of the strengths of ionic bonds? Well, let's look at this equation. So there are two main things that matter. So first is the charges, Q1 and Q2. The charges here mean, for example, for sodium and chlorine, if sodium is 1, Q1 is plus 1, and Q2 is minus 1. So it's just whatever the charge is on that ion. And so this is going to differ if we have, say, calcium chloride, CaCl2. Now we have a Q1 of plus 2, whereas Q1 is still minus 1. Right, so these charges matter. So the bigger the charge means a stronger force holding them together, or a stronger bond. Right, so things that are more highly charged will give a much stronger attraction between them. And this is reflected in the solubility rules, that things with very high charges tend to be less soluble because it's harder to pull the ionic bonds apart when you put it into a solution of water. Right, so that's one thing. So we can see, for example, if we look at the compounds, look at a bunch of chlorides, say we compare sodium chloride versus calcium chloride versus iron chloride, iron 3 chloride, just to pick 3 examples here. The strongest bond is going to be this one, simply because iron has a plus 3 charge here. This one will be in the middle, calcium chloride, because we have a plus 2. And this will be the weakest of the bonds in sodium chloride, because it's only a plus 1 charge. Right. The negative charge on chlorine is the same for all three of these, so we can directly compare them and just think about the charges on the positive ions. Okay, so that's one part of our equation. The other part is D. And D here is how far are the charges apart from each other. So our cations would tend to be smaller than our anions, and we're thinking if you take the middle part, D represents this distance here. So the closer the ions can get to each other, the stronger their bond will be. The further they are apart, the weaker their bond will be. Now, how is this reflected in terms of ions? Well, it's going to be dependent on ion size. The bigger an ion is, the less close those centers of the ions can get to each other. So smaller ions have stronger bonds, stronger ionic bonds. All right. So if we say, look at, we'll stick with chlorides, but if we compare, say, lithium chloride to sodium chloride to potassium chloride, so here I'm just taking the alkali metals and just going down the periodic table. So this should be our, lithium will be our smallest because it's at the top of the periodic table, whereas potassium is our largest. We should see a trend that this lithium chloride should have the strongest bond of these three, whereas potassium chloride will have the weakest. And this is simply due to the size of the ions and how close they're able to get to each other. So the closer the ions can get to each other, the stronger the bond will be. So we have these, both of these factors matter for the strengths of ionic bonds. There's no set, in ionic bonding, we don't think about single versus double versus triple. That's not really relevant. Instead, we think about the charges of the ions and then how big those ions are to let us know how strong these forces are that hold them together. So that's it. That's all we're going to talk about with ionic bonding. This is not going to be a huge point of emphasis, but I want you to make sure that you're familiar with it since it does come up.